Welcome aboard, where aviation concepts become simple. From instruments to aerodynamics, we make exam prep clear and cockpit learning faster. This is StudyKwik Aviation.
Welcome to StudyKwik, your quick and easy source for aviation knowledge. Today we begin a very important topic in high-speed flight, the Mach Meter. This instrument is vital for pilots flying near or beyond the speed of sound. Understanding the Mach Meter will help us grasp both the science and the practical challenges of modern aviation. We'll explore the speed of sound, how it changes with temperature, how the Mach Meter works, its construction, and the types of errors that can affect it. Let's begin with the concept of the speed of sound. As an aircraft accelerates towards the speed of sound, shock waves begin forming around different parts of the aircraft. These shock waves bring significant effects like increased drag, buffeting of the airframe, a noticeable reduction in lift, and sometimes even sudden pitch changes. Pilots may also notice that control effectiveness is reduced at such high speeds. The speed of sound itself is given a special name, Mach 1.0. But here's the important part. Mach 1 is not a fixed number. It varies with temperature. When the air is colder, the speed of sound reduces, and when the air is warmer, the speed of sound increases. This is called the local speed of sound, or LSS. At sea level, under ISA standard conditions of 15 degrees Celsius, the local speed of sound works out to 661 knots. But as soon as the temperature changes, so does this number. That is why the Mach number is a ratio and not an absolute speed. We calculate LSS using a simple formula. It is 38.95 multiplied by the square root of the static air temperature, measured in Kelvin. Remember, to convert Celsius to Kelvin, we just add 273. For example, if the outside air temperature at cruising altitude is minus 50 degrees Celsius, we convert it to Kelvin. Minus 50 plus 273 equals 223 Kelvin. Put this into the formula, and we get 38.95 times the square root of 223, which is approximately 582 knots. Now let's confirm this with a CRP5 navigation computer. If we set the Mach number index to minus 50 degrees Celsius, we then locate number 10 on the inner scale to represent Mach 1.0. On the outer scale, the reading is 582 knots. This matches our manual calculation, proving the formula works. So, what does the Mach meter actually show? It does not display true airspeed directly. Instead, it shows the ratio of the aircraft's true airspeed to the local speed of sound. In other words, it's giving us a fraction. If the aircraft is flying at half the speed of sound, the Mach meter reads Mach 0.5. Now let's talk about the principle of operation. Static pressure from the static port enters the case of the instrument, while the pitot tube feeds pressure into the airspeed capsule. The capsule expands and contracts with changes in dynamic pressure, and this motion is transferred through a system of links and arms. But the Mach meter also contains another capsule known as the altitude capsule. This expands and contracts with static pressure as the aircraft climbs or descends. The movement of both capsules is combined through a mechanical ratio arm, and the resulting movement drives the needle of the instrument. The genius of this design is that the Mach meter automatically compensates for changes in altitude and temperature, giving the pilot a direct reading of Mach number instead of raw airspeed. That's why it's much more useful than a normal airspeed indicator at high altitudes. Now let's look at some of the errors that can affect the Mach meter. The first is instrument error. This occurs because of small imperfections in manufacturing, tiny amounts of friction, or even play in the linkages inside the instrument. The second is position or pressure error. This happens because the pitot and static ports are placed in locations on the aircraft that may experience turbulence or disturbed airflow, especially at certain angles of attack. Another type is maneuver-induced error. When the aircraft suddenly changes attitude, the airflow around the sensors may temporarily fluctuate, giving a slightly inaccurate reading. Interestingly, the Mach meter does not suffer from density error. This is because both dynamic and static pressures are affected by air density in the same proportion, and when the ratio is taken, the effect cancels out. Now that we understand the basic working principle of the Mach meter, let's explore why pilots rely on Mach number rather than airspeed during high-altitude cruise. At low altitudes, air density is high, and airspeed gives a good indication of performance. But as an aircraft climbs into thinner air, true airspeed may be high while the indicated airspeed is much lower. If a pilot relied only on indicated airspeed, the aircraft might accidentally exceed critical Mach number without realizing it. Critical Mach number is another key concept. It is the lowest Mach number at which airflow over some part of the aircraft first reaches the speed of sound. This doesn't mean the whole aircraft is supersonic. It means only a small region of the airflow has gone supersonic, while the aircraft itself is still below Mach 1. But the moment this occurs, shock waves begin to appear, and aerodynamic problems follow. As the aircraft goes faster beyond critical Mach, shock waves grow stronger, drag increases rapidly, lift reduces, and control surfaces become less effective. This is why pilots monitor Mach number very carefully at high altitudes. It provides a true measure of how close the aircraft is to compressibility effects. Another important factor is temperature. Because the local speed of sound depends only on temperature, not altitude directly, the same Mach number may correspond to very different true airspeeds depending on conditions. For example, at high altitudes where the air is cold, Mach 1 equals a lower TAS compared to warmer conditions at the same height. This explains why pilots use Mach number to set cruise speed rather than knots. Airlines often publish cruising Mach numbers in their flight operations manuals. For instance, an aircraft may be scheduled to cruise at Mach 0.82. This ensures consistent performance regardless of the outside air temperature. Let's imagine a real example. Suppose the outside air temperature is minus 50 degrees Celsius, and the aircraft is flying at a true airspeed of 480 knots. The local speed of sound at that temperature is about 582 knots. Divide TAS by LSS, and the result is 0.82. So the Mach meter would read Mach 0.82, which matches the planned cruise. In modern cockpits, the Mach meter is often combined with the airspeed indicator into one instrument called the airspeed Mach indicator. It automatically changes over from showing knots to showing Mach number once the aircraft climbs beyond a certain altitude. Usually around transition levels of 200 to 300 knots indicated airspeed. This saves the pilot from having to mentally convert between the two. Now let's move deeper into the construction of the Mach meter. Inside the instrument, the pitot pressure capsule expands with increasing dynamic pressure, just like in a normal airspeed indicator. But the altitude capsule, which responds to static pressure, provides a correction factor that adjusts the reading according to the density of the atmosphere. These two capsule movements are connected through a differential linkage system, often involving cams and levers that mathematically convert the ratio of pitot pressure to static pressure into a pointer movement. The dial is then calibrated in Mach numbers rather than in knots. In older, purely mechanical instruments, this system required very precise engineering. The capsules had to be thin enough to expand under small pressure changes, yet strong enough to withstand repeated cycles. Any friction or backlash in the gears could introduce errors. That's why regular calibration was necessary. With modern avionics, the Mach number is calculated electronically by the air data computer. The ADC receives pitot and static pressures from the aircraft's air data probes, measures the outside air temperature, and then performs the calculation digitally. The result is displayed on the primary flight display as Mach number with great accuracy. Even with digital displays, the principle remains the same. The Mach number is simply the true airspeed divided by the local speed of sound. The only difference is that electronics now do the work instead of mechanical linkages. Pilots also need to be aware of certain limitations. For example, during very rapid climbs or descents, the Mach indication may lag slightly behind the actual value. This is because pressure sensors take a small amount of time to stabilize. In extreme maneuvers, transient errors may appear, but they quickly settle once the flight path stabilizes. Another factor to note is that while the Mach meter cancels out density error, it still depends on accurate temperature sensing. If the outside air temperature probe is iced up or malfunctioning, the computed Mach number may be slightly off. That's why regular checks and maintenance of sensors are so critical. Let's now summarize and put everything together. The Mach meter is not just another dial in the cockpit. It is the pilot's window into the world of compressibility effects, shock waves, and high-speed aerodynamics. It tells us how close we are to critical Mach and ensures we remain within safe speed limits. Remember, Mach number is a ratio, not an absolute speed. It depends entirely on temperature. At colder temperatures, the speed of sound reduces, and so the same true airspeed will result in a higher Mach number. This is why aircraft operating in cold, high-altitude air must be extra cautious. We also saw how the Mach meter works, combining pitot and static pressures either mechanically with capsules and linkages or electronically with air data computers. We explored the common errors: instrument error, position error, maneuver-induced error, and noted that density error does not affect Mach meters. We discussed why pilots prefer to fly at a constant Mach number during cruise. It gives stability in performance, efficiency in fuel burn, and safety against exceeding critical Mach. Airlines therefore publish cruising Mach values like 0.82 or 0.85, which become the standard reference for the flight. Finally, as aviation technology continues to evolve, the importance of Mach number only increases, especially for aircraft operating near transonic and supersonic speeds. Whether you're a student pilot, an engineer, or just an enthusiast, knowing how the Mach meter functions gives you deeper insight into the challenges of high-speed flight. Thank you for watching this detailed explanation on StudyKwik. If you found this lesson useful, don't forget to like the video, share it with your friends, and subscribe to StudyKwik for more clear, simple, and practical aviation knowledge. Keep learning, keep flying, and see you in the next lesson.